อืม Hello, audible?
Yes, sir. Yes, sir.
Okay, so now we continue this. So see, some other question I need to ask. Let us be practice also this question. Okay. Yes, please. So this way, okay. Suppose this first part. This is the with reference to the voltage variation profile caused by the load change imposed on AC generator when steering a large motor. Starting a large motor. So you sketch this voltage drop and then silent state factor the causes of variation of this part. Why it is varying? When it is overload, then voltage is dip because current is increased suddenly. That's why it depends on current, power factor, what is the starting current of motor, what is the method of starting of motor, then how to recover. So your AVR will help in that. Correct. So actually, there is a one characteristic diagram is there. Okay, this shows this instantaneous voltage drop, IVD, on alternator. Okay. So here, this is your constant voltage, this V. In this diagram, this is your your voltage reference line. Okay, reference value. Okay. But when we start, suppose at this time of t equals to 0, this t equals to 0, okay, we start the motor, large motor, then due to large current, this terminal voltage of alternator, bus bar voltage goes down. So this V1 is the voltage dip with respect to your reference voltage, okay, value. This is your voltage dip. Then this will start to recover after maximum dip. Then it goes above this reference, beyond this. So it is overshoot. This V2 is maximum transient voltage overshoot, means it is above the reference voltage. Then it again goes down, means it is get some one cycle. Then it becomes steady state with there is a percentage plus minus percentage error. Okay, so this is this part. This voltage is V3 is the recovery voltage. See, earlier your voltage is this value, like 100 volt, or maybe it is like 440 volt, and then there is a down percent, 100%. Then there is a how much percent? A maximum 85% is goes. At least 85% voltage available at the motor terminal. Then it recovers and overshoot with V3. Then it goes down, okay, and stable, steady state value. So this V4 is steady state voltage regulation. Now there is a variation here. Hello, V4 is the voltage regulation. Means variation, your reference value to this value. So this V4 is the percentage voltage drop. Okay. V3 is recovery voltage after this value. What is the value? Means suppose it is a 440 some value. Now this is your another here, this V3. Okay. So suppose V is the reference value. Now V3 is your recovery voltage. So what is the variation here? Then this T0 is the time at which your motor is started, and T1 is the recovery time. T2 is time to recover and remain the constant. Okay. Just you make this diagram and you write this time and voltages, what are the factors, because it depends on the motor, what is the method of starting of motor on, it is direct online starter or it is star delta, what is the power factor, correct? Okay, dear. Okay. I will put this, I think it is already put in the group. Next is a total load of 800 kilowatt. This 8.8 power factor supplied by two machines. So let us, there is a second question. There is a two alternators. They are running in parallel and sharing a total load. So they are operating in parallel. This is the total load on machine. It is 8,000 kilowatt total load. 8.8 pure factor. This is your bus bar. This is machine 1, alternator 1, suppose. Or A, B, C, you can write. 2. Now we say that if the load on one alternator, suppose first one, it is 600 kilowatt at 0.9 power factor lagging. Okay. What is there is a kVA rating. kVA 2 it is asking, and power factor. Okay. Very simple actually. So it is a total load You write here parameters. So see, kilowatt load, then their power factor, then we can calculate their kVA load, kilowatt load. Okay, this is on alternator 1 and this is on alternator 2. Now load on alternator 2 equals to total minus shared by machine 1. Correct now? Here this is total kilowatt load. There is a total, you write here total load. This is your on alternator 1, this is on alternator 2, okay, like this. Okay, this is your parameters, you can write load parameters. Here this total load is 800 kilowatt, power factor is 0.8, then kilowatt load is, this is your kilowatt by power factor. So it comes, if you do this 8000 by 0.8, it comes 10,000 kVA. Now my dear, on machine 1 it is given 6,000, power factor is 0.9, then kilowatt load is, and this is kilowatt A. Okay, what is the kilowatt load? Sorry, not kVA, please. This is kVA of machine A of 1. So it is your kilowatt 1 by power factor 1. Okay, this one. It is 0.9. How much it comes?
6666.
Great. 6.67 kVA. Then we calculate what is the load on kilowatt load on 2. Kilowatt 2 is total 8 minus 6. We get at 2000 kilowatt. Then we calculate kVA load. kVA 2 equals to total kVA is 10,000 minus shared by this machine. Okay. Four times 3 kVA. Okay, this much. Now we can therefore we can calculate the power. So this is the rating, kVA rating of machine 2. Then power factor cos phi 2 will be kilowatt 2000 divided by kVA. 0.6, okay. Correct. So you can write this kVA rating and power factor of machine 2. is a one practical question. This will give the good idea about your third question. Briefly explain this power. You know, in AC, circuit. So it is question number 3. AC circuit. Now this AC circuit is 3-phase or single phase and 3-phase. So here, you know, the powers. Okay. There is a 3 types of power. Are there active, or it is true power. Second is reactive, or reactive power. Third is apparent power or total power. Okay. Apparent is denoted by S, this is by Q, this is by T. So suppose, you know, in a AC circuit, it is not a pure resistive. It may be resistance and your inductance. Resistance and inductance. So your load is made of resistance and inductance. Okay, this is your load impedance. Okay, when you apply the power, correct, means this is your load impedance. Okay, load impedance is take a load current. Here is the apply voltage V. Correct. This is R. This is X. Now you know impedance. If this load impedance triangle. Okay. Resistance, reactance, and this is Z. This is the phi. Okay. So this true power means it is the power dissipated in the circuit resistance. Means it is P equals to I square R. Okay. Now if we put a here value, this you know cos phi. If you apply here cos phi, it is R to Z ratio, power factor. Then R is Z cos phi. Correct, no? So if we put here value, this I, we put a like this I into I, it is Z cos phi. Okay, this is your R. Now you know IZ means total this voltage across the impedance into I cos phi. Okay, so this is the active power, VI cos phi. Okay, the unit is watt, bigger unit is kilowatt or megawatt. Then reactive power is developed across the circuit reactance, means it is I square X, and denoted by Q. And this is if you also apply here sin phi equals to X to Z ratio. So again it is VI sin phi. Reactive power, the unit is volt ampere reactive. So it is voltage into current reactive, or bigger unit is kilovolt ampere. kVA reactive. Okay. So this is the unit of this power. Apparent is, in AC circuit, always the values written or measure, that is RMS value. So this is actually this apparent power is nothing but it is the product of RMS value of voltage to RMS value of current. RMS values, okay? Product of. Correct. And this unit is volt ampere or kilovolt ampere. kVA, right? Okay. This is your PQR. Okay, this is your P. This is your Q. Q equals to BI cos phi. Okay, and this is your S. Now there is a power triangle also. Active power. This is reactive power. If it is, like reactance is two types. If XL, it is upward. If XC, it is down. XC is negative. This is positive. This is negative. That's why we write Z equals to, hello?
Sir,
Yeah.
Q is equal to VI sin pi, na?
Q equals to,
VI
yes.
sin pi.
Yeah. Well, now, here we write impedance. This is a, complex number, that is R plus J plus minus. This is maybe this reactance is positive or negative. Means actually circuit reactance is maybe inductive or capacitive, lagging or leading. Same like reactance, your reactive power is also two type of nature. Okay, if it is inductive reactance, then plus positive Q. If negative, no. If capacitive reactance, then it is minus Q. Okay. But if suppose positive Q means the power factor is lagging. Okay, this is your 5. So here is the active power P means kilowatt. This is the kVAR. This is kVA, apparent power. P, Q, and this is S. Correct? Okay, dear. This is your power there. Now this S is also called as a complex power. It is like we can write this real part, this is imaginary part. Or as we can calculate like this, P square plus Q square by Pythagoras, because it is a right angle triangle. Okay, or means kVA equals to kilowatt square plus kVAR square. Okay, this. Correct? Then power factor. Power factor is defined power factor. Okay. Cos pi. So actually, the definition are, the in a circuit voltage and the current. If there is a phase difference in voltage and current, phi, then cosine means sine of, cos. Cosine of phase difference angle, phase angle, okay? Phase angle between voltage and current. It is cos phi is your power factor. Second, impedance triangle, we can write cos phi is R to Z ratio in an impedance, or it is apparent power to kilowatt by kV. This will give the power factors. Okay. Now, why we improve the power factor? There was a large question was asked in your ETO. In power, it is written in power, switchgear and power. Okay, also method to why, what is the power factor correction? Why it is required to improve the power factor? What is the advantage of or high power factor means power factor correction? What is the method of power factor correction? Here we cover this. Here it is only ask the definition, but I am explaining you. Hello. So any load you take, suppose you take a 3-phase induction motor. It is an electrical load. Okay. When it is connected to your supply, it draw the power. Okay, so what is the rating here? Suppose it is in kilowatt. This is the mechanical load on this. So what is the kilowatt load here? Then according to motor, draw the current here, line current, load current. So this load current, or either you simple circuit you can make like this is your load, kilowatt load, this is voltage, then this is load current. So if we calculate this load current equals to your kilowatt rating into 1000 to convert into watt. Then if it is 3-phase, like motor, then you root 3 VLI, VI we have calculated cos phi also. Then in case of motor, because this is output side load. Now motor drawing from input side. Okay, then you also divide by motor efficiency. Okay, then you get a load current. For here only just we write per phase, then V cos phi only. Okay, so generally other like load is fixed, motor efficiency fixed, then other parameter voltage is fixed here, line supply voltage. Then basically your load current in circuit is inversely proportional to power factor. Okay. It means in short, if power factor is, let us be suppose why we improve means if low, suppose, or correction means we take an advantage, then high you can take. Disadvantage of low power factor, please, what you want? Advantage of high power factor, why we improve? So if your improve means higher value, like 0.9, low is 0.8, 0.7. So if we improve the power factor, then what happens? Your load current in circuit is reduced. If load current is reduced, then you are due to loss in the circuit, power losses. Your I square R loss because current, so these losses are reduced. Losses reduced means efficiency is increased. Okay, so this is one. Second, another also, if power factor is high, current is low, voltage drop in circuit, VI, IR or IZ, okay? VD, voltage drop, IZ or IR, it will be reduced. It means the load get a sufficient voltage. Due to this, there is a circuit resistance also, by this cable resistance also, then motor terminal voltage should be good. Okay, then good voltage means we get a rate.
Power factor is increased, then IL will be decreased.
Which one?
Okay, sir.
IL means load current is decreased, then drop is decreased, means rated.
Okay, sir. Okay, got it.
rated terminal voltage at the motor terminal voltage. It means good performance. If the motor terminal voltage is decreased, then motor draw the more current. Then there is a losses, further increase in the losses. Okay. Third, you can also like your electricity bill. So energy conservation, conservation of energy means saving. सेकेंड उससे क्या होगा आपका इलेक्ट्रिसिटी बिल रिड्यूस. ओके. रिडक्शन means cost saving. Okay. It is to take a meaningful item because suppose per hour you have how many, like in a suppose annually your motor is operate 8,000 hours, and per 1,000 you suppose you save the like 1 kilowatt, or maybe let us fraction like 0.5 kilowatt. Then in 8,000 hours there is a use unit kilowatt hour. If you multiple this total annual hours, so there is an annual hour saving, then annual cost is reduced. Okay. So this is the advantage. That is why we improve the power factor. Now how we do the power factor correction? So suppose your alternator in system, electrical system, bus bar or whatever, they have a generally 3-phase supply. Okay. This like correct. Okay. But your loads are generally on this. There is a generally transformers, 3-phase transformers. Okay. Transformer, induction motors also there, 3-phase induction motor. Some lighting loads is there. But lighting loads are considered as a unity power factor. Unity power factor. But they are have a lagging. Okay. My dear, generally the lagging means reactive loads. Lagging power factor they have. Okay. Power factor, lagging power factor means inductive loads. What is the property of inductive loads? They draw both active and reactive power. This motor, they required active and reactive power. Means your inductive loads draw the active and reactive power, and your alternator fulfill the demand. Suppose this is load 1 is take a P1 Q1, this take a P2 Q2. Then this alternator supply active and reactive power. Okay, this P is the useful power, true power. But if Q is due to low power factor, this Q is increased. If suppose Q is increased, lagging kVAR. Actually, this Q, kVAR, reactive power, it is also 2 types. Positive, negative. Positive is also called as a lagging kVAR. Lagging means it is in inductive loads. Lagging. This is leading. This positive Q, negative Q. Okay. Leading due to it is due to capacitive load. Capacitive loads are capacitive. If loads are inductive, then if circuit is inductive. So now if we calculate your total load, there is a motor loads and lighting loads. If we calculate total loads, so total active loads, we add this all active loads. We add all reactive load, reactive power. This is the Q total. This is called as a kilowatt load, total kilowatt. It is fixed. This is the real. Now their vector sum will get apparent power kVA. Okay, this is your 5. If this is 5, then this is your kVAR 1, suppose, corresponding to this, there is a kVA 1, this, okay, here to here. Now due to this, this, if you suppose it is a cos phi 1 is suppose 0.8 lagging. Now we want to improve this power factor phi 2 by 0.9 lagging. Then this angle is reduced. How it is reduced? By introducing the capacitive kVAR, leading kVAR. So here, if your power factor is low, means inductive, this reactive power is high demand, positive type, positive thing. Okay. Then what happen? Either if you take a static capacitor bank, suppose you take a capacitor bank that is maybe like it is connected in like this, but it has a fixed value of capacitor bank, okay, like this. This is your capacitor bank, or it is called as a capacitor bank, or it is called static capacitor, statics, VAR. So now, my dear, what is the property of this capacitor bank? They take a small active power for their activation, but they supply negative Q to the system. Means they have a negative kVAR, okay, reactive power. So means there is a negative, this much is negative Q will come due to this capacitor. Now about this magnitude, like here, this is equals to this, okay. This part is reduced from here. Then your net kVAR is reduced. Then corresponding to this demand, this is your new kVAR. Now your net kVAR is reduced to 2. Corresponding to this, your kVA load is also reduced on the system, and this angle is reduced phi 2. If angle is narrow, power factor is high. Like in transformer, no load power factor is large. Okay, this is low. The we improve. Okay, this is reduced now because it imposed. So this by static capacitor. Other method is it is automatic voltage automatic power factor correction. Automatic power factor correction panel, APFC panel we are using. Okay. Second, we can use the synchronous 3-phase synchronous motor. Okay, that is synchronous condenser. It is called. Why the 3-phase motor is called as a synchronous condenser? Hello. See, if we talk about the 3-phase synchronous motor, okay, it is it required a DC excitation. DC excitation is required. Correct. And there is a supply also. Is 3-phase AC, okay? Stator supply 3-phase AC. Here, correct? So it required DC excitation. Now the power factor, suppose it is operated at no load. No load. Its speed is synchronous speed. Now, actually the power factor of induction motor is always lagging. Okay. But the power factor of three-phase induction motor depends on three-phase synchronous motor. Synchronous motor depends on excitation. Okay. It means there is a under excitation, the normal excitation at normal excitation, or over excited. Okay, excitation. If we improve here DC, okay, DC excitation, then current IF is increased. Under excitation means low value of field current. Okay, it operates at the power factor is lagging power factor. At normal, if we increase then a particular excitation, it start to operate at unity power factor. Then if we further increase the excitation, we start to operate at leading power factor, leading. Okay, dear. So at lagging, it take the both active and reactive, both are plus. Okay, but here only active power, no reactive power involved. Okay, dear. Here it take active power, but there is a negative Q. Okay, correct? Then it means if we operate this three-phase induction motor parallel with this other loads, means on same bus bar, like this is your distribution transformer, okay? Then this is your common bus. Here the number loads are connected. So on same bus bar, we operate this motor, synchronous condenser. Okay. So we it to improve the power factor. Here before this motor only, okay, not in downstream, okay. That's why it is also where we take capacitor bank, okay. That's why your three-phase induction motor in overexcited state, it operate at leading power factor and it start to give the supply reactive power to bus bar. Then the power factor is improved because net reactive power is reduced. Okay, correct? Now this question here is a part of the second part is show only these things. the alternator which is rated is connected to bus bar here we measure kilowatt. There is a multi function meter, a measure active, reactive, power factor, everything. Or either you have a kilowatt meter and power factor meter, okay? Power factor meter. Then there is a load is connected on this bus bar, okay? This is your load. Now this alternator is what is the given? 750 kVA rating at 0.85 lagging power factor, okay? Now we say that what is the maximum load on kilowatt that we can put without it overload at this power factor is the first part of this question, maximum kilowatt load that we can put on alternator. So this kilowatt load equals to kVA rating into rated power factor 715 to 0.85. Okay. 637. This is okay. 637. 637.5 kilowatt. Then second, he said that if actual operating parameter, what would be the overloading the alternator if kilowatt reading is this and power factor reading is this. Actual operating kilowatt reading is 620 kilowatt, okay, and power factor is 0.80. So we can calculate the actual kVA load on alternator equals to kilowatt load by power factor 620 divided by 0.8. How much it comes?
775.
775 kVA. So what is the rating? 750. So this kVA load on alternator is increased. That's why one another disadvantage of low power factor here. Hello, please you write here another disadvantage. Fourth one. Total or apparent kVA load on system or either on alternator. System means electrical system. On system is decreases if you increase the power factor. Decreases means, see, if low power, like here See, if our power factor now, earlier it is 0.885, now it is 0.8, the KVA loads are higher. Then your alternator is overload. So yes, there is a overload. Alternator is overloaded. Loaded by 775 minus 750 is the rating, 25 kVA. So higher load, it is supply the higher kVA load, okay? So this is the disadvantage of low power factor, okay? Yes. Now we take this droop is another very important thing. Maybe they ask the question on this numerical, because it is also asked in MET also this topic droop. So now we in second part we take a droop. Please. That is, I'll take here 2 minutes break, okay? Just please do not leave the meeting. Hello, audible?
Yes, sir.
Yes, one another very important topic related to this synchronous machine. Okay. This is asked in ETO, but there is a, in MET also this numerical on this group setting. It is asked group. Like here, he said that with reference to diesel engine driven alternator, what is the significance of term speed droop during parallel operation? So this droop, speed droop or droop, speed droop curve, speed droop characteristic, you can say. It play important role when two machines are operating in parallel because it affects the load sharing, means it decides the load load on machine. Okay. Now he said that assume two alternators operating in parallel, then you outline this droop characteristic. And what is the droop characteristic? Actually, it is frequency versus load curve. Okay. So I will explain first with single machine. Let us, you consider there is a single synchronous machine alternator. It is connected to load. Load is connected here. This is your at this bus bar. Suppose this is the bus bar voltage and frequency. Sorry, this is your bus bar. Okay. Bus bar voltage and frequency. Okay, and this is your alternator. Now this is the load we vary in kilowatt, suppose on alternator. Okay, so just of your guidance, as we put the load on alternator, the speed is decreased. If the speed is decreased, then frequency is directly proportional to speed. So means this bus bar frequency is decreased. Okay, so let us, if we draw this kilowatt load versus frequency, this is frequency. Now this frequency or speed, frequency versus load. This is kilowatt load. Like here 0 kilowatt load, then here it is 200 kilowatt, 300, 400 kilowatt, then it is 600, then it is 800. 400, 600, 800, then 1000. This is your kilowatt load. Okay. Suppose it is 1000 kilowatt rating is maximum load, a full load. Frequency. So as suppose this load is not put here. Now it is operating at no load. So what is the no load frequency? It is we set a slightly higher. There was a question also in here. If you read, hello. Here, see. If means why incoming generator frequency is higher than the bus bar frequency, means before we connect to the bus bar, we maintain a high frequency. There was a question in first here. Explain how it is function as a synchronous capacitor. Here is the sixth question was given over already. There was one question, please. Generally, there is a question why we are maintaining the same power factor of alternator when two power alternators are operating in parallel. There is a why this higher than alternator. Before it take the load, we set a higher frequency. Why? Because as this alternator carry the load, loaded, as we load, put on the load this alternator, then the speed is decreased, means frequency is decreased, okay? So this is your no load frequency, okay, F naught. But now suppose at zero load, let us it is 62 hertz, okay? Sorry. Is F naught is 62 hertz. Like this. Okay, and rated maybe suppose it is 60 hertz or whatever it is, okay? Now we can do. Now as we put 200 kilowatt load, this is kilowatt load. So now corresponding to this, there may be drop in frequency and this is the load. Same like for this 400 kilowatt, then this is the drop in frequency here. So it comes here, like then it comes here, then it comes here, then it comes here. Okay, so this dot we get this. Now if we join this all the dots, we get this curve. Okay, dear, this curve. Okay, so this curve is called, this curve is called frequency versus load curve or speed versus load curve. That is known as a speed droop. Why? Because frequency and speed, it is called a speed droop. Okay, curve. This is frequency versus load curve. Okay, correct. Now, what is the full load here? 1000 kilowatt. Then what is the frequency? This is not zero frequency. It is a full load frequency. So my dear, from here to here is drop in frequency. Hello. Now we can calculate drop in frequency from no load to full load. No load to full load, like voltage regulation, same like it is a speed regulation. Actually, this speed droop is called speed regulation, like voltage regulation from no load to full load. Speed regulation means speed droop, okay? Percentage speed droop, okay? It is called percentage speed droop, okay, my dear. That is nothing but it is now because speed means no load speed minus full load speed. Full load speed divided by no load with respect to no load. Now this, because frequency is directly proportional to speed, then we can replace in terms of frequency we can tell. Okay, dear, and percentage it is 100. Okay, so actually this is called a speed droop, percentage speed. Either it is like a 4% or it is 3%. Okay, that is called speed droop. Okay, got it? So it is a drop in frequency. Okay, from no load to full load. Now, if single machine, nothing is if you change the droop setting, means what happens? Suppose if we increase the droop setting from 4% to 5%, what happens? This curve is slope is increase. Hello, it shift towards the down, like for same kilowatt more drop. Now see, this is the 4,000 kilowatt. Now what is the frequency? 1000 kilowatt. What will be the frequency for 1000 kilowatt? This Correct, na? So now this the drop in frequency is increased. Means percentage this speed drop is increased. Like it is now it become 5% or 6%. Okay. Correct, na? Okay, dear. Now this play the important role when two machines are operating in parallel. Okay. Now we come to the question. So now you consider two machines or alternator are operating in parallel and sharing a total load. That is their group setting are maybe or same identical machine. Okay, two identical means their same group setting. Okay, so like alternator 1, alternator of 2, machine 2. Okay, their kilowatt rating or kV rating, capacity are same. Was 1000 kilowatt. This is also 1000 kilowatt. Percentage drop. It is called speed drop. Drop setting. Speed drop setting is 4%. Here is also 4%. Suppose. Then and suppose no load frequency is 60 Hz, 62 Hz. Okay. Correct. We take an example, identical machine. So let us do when two machines operating in parallel and sharing a total load. So what? If we vary the load, then this is the alternator. What is the percentage? Means load shared by machine 1 and 2. Machine 2. Okay. So my dear, first here we take a machine 1. Here we take a machine 2. Okay. Both are like suppose this is the total load in kilowatt. So total capacity 1000, it is like a 2000 kilowatt total kilowatt. Like this is the midpoint of 1000 kilowatt. Here this is the frequency. Here we take a kilowatt load. Okay? Load on machine kilowatt. My dear, if suppose they have a same, this is the no load frequency like 62 Hz F naught. Okay, both have same. Now, if their group setting are same, means their lines, their characteristics. Now, if we draw characteristic, this here that total kilowatt load. So this is your operating point. Okay, now load shared by machine 1. This is the kilowatt 2. This is kilowatt 1. Okay, they are equal. See, they are equal. This is the characteristics of machine 1. This is characteristics of machine 2. So they are here total load equally if their droop setting are equal. And what is the operating frequency at this full load operating point? This is the operating point corresponding to this is the frequency F. It may be 59 or maybe 60 hertz, whatever it is, okay, like this, less than this. This is the percentage droop, and it's from here to here. Okay, dear. Now suppose let us now we increase the droop setting of machine 1. Increase means droop setting is increase means for same load the drop is more in frequency or speed. So if this is slope is down of machine 1 line, this characteristic is down like this. So now this operating point shift here in this case. So when the blue this kilowatt 1 here is kilowatt 2. This here the same kilowatt load. But now if droop setting is increased, now we see this kilowatt 1 is reduced, kilowatt 2 load on machine 2 is increased. In this case, kilowatt 1 is less than kilowatt 2. So your machine 2 is overload. It takes the more kilowatt. It's here a more kilowatt load. Correct?
Kilowatt
And,
number 1 will take less.
yeah, droop setting is increased. They take a less load.
Yeah,
Now
that's why this opposite sign will come. Sir.
no, please, it is different. Okay. Now this is now operating point. Now see overall frequency also drop. Okay. If droop setting is change. Okay. Correct. So this is the droop setting. What is the speed droop and how is significance of droop setting when two machines are operating in parallel. Correct, no?
सर मशीन 1 का स्पीड ड्रॉप सेटिंग्स इंक्रीज किया राइट सर?
Yeah, if increase load, it take a less load. Okay. Now this diagram. Now maybe the machine. We take one example here. This question. Now this characteristics we can show like this frequency is common for this. Hello. Now suppose this is your frequency line. Okay. Let us your machine 1. Their droop setting are same. Then see machine 1 is suppose 1000 kilowatt. Machine 2 is only 800 kilowatt. So this is real. Now this is your frequency or speed. Here suppose this is the no load frequency. Okay, 60 hertz. It is not. This no load frequency is given 62 hertz. Okay. So if they are operating at full capacity, their individual load characteristics are this. This and this. Okay. So here this is your kilowatt of machine 1, that is 800 kilowatt. Suppose this is 1000 kilowatt. Okay. So if they are at full load, this is the droop setting. Now here, hello, what is the frequency here? This is the frequency. Now your frequency is down here like this. If they take the load, their frequency is down here. Okay. So what is the frequency at this point? F. Okay. Correct. So this is the machine 1. This is machine or alternator. This is 2. Now there is a one here example is given as so suppose here 2 3-phase alternator this. Okay. Suppose 2 3-phase alternator operating in parallel, rating of A and B 1000 and C. So here alternator A. So suppose this is machine A, this is machine B. Okay, you write. Alternator A, alternator B. Their rating means capacity. It is 1000 kilowatt. This is 800 kilowatt. Now we say that their droop setting of both machine. Droop setting. Is 4%. Here is also 4%. Then no load frequency is given 62 hertz. Suppose. Then we can calculate. This percentage. This droop means percentage speed regulation frequency. It is given. Then what is the drop in frequency? Total drop in frequency. Can we calculate? It is 4% of no load frequency. 4% means 0.4. Here it comes 2.48 hertz. Means what is this total drop here to here? What is this drop in frequency? 2.48. 2.48, okay, hertz. This, okay, drop in frequency from here to here. Correct. Now, if load on one machine, total load, okay. So, what is the total capacity here available in this now? Now, we say that if total load is only 1000 kilowatt, then he say what is the kilowatt load on machine A, machine 2, and what is the frequency of this bus bar at this load? They ask this type of question. So, my dear, if they are operating at full load, this frequency is, what is the frequency here? This minus this drop you can calculate, no? This minus this with this, then this equals to, it is 62 minus 2.48, correct, no? What is the bus bar frequency when there is this total load is 18 kilowatt? Means if they both machine are operating at full load, what is this bus bar frequency?
59.5.
Yeah, 59.52 hertz. Okay, but my dear, total load is only 1000 kilowatt. Means, so see, below this line is not. If we can say 2000 kilowatt. If total load is 2000 kilowatt, where they operate the load? They come from this down. Means slightly they overload. Correct? Both machine are overloaded. So this is your 2000 they can see here. No? Then this is the characteristic. And this will be your frequency. Correct? Now this is the 2000 kilowatt. Because this plus this 1800, then they take a 100 kilowatt more. Correct? Like this. Okay. But now your load is only, what is the load? 1000 only. Then where they operate above this point, no? Like here or here. Maybe suppose this is your total load. If this is the total load, that is how much it is? 1000. Total load this. Then let machine 1 is share X kilowatt. Then this will share how much? This machine. Okay?
1000 minus.
Yeah, 1000 minus this machine will share. And let us this at this point, what is the frequency? Let us it is F. Now here to here, now this here to here. What is the draw? This height? It is 62 minus F. This no. Here also same. If 62 minus 59.2 you do na, you get this. Okay, 62 minus 59.52 na, it will give you 2.48. Same like here it is F, operating frequency. So let both machines are operating in parallel, and the here total kilowatt load is 1000 kilowatt. Let X is the kilowatt load shared by machine A. Then 1000 minus X kilowatt will be shared by machine B, and let F is the bus bar frequency. Okay, bus bar frequency at this load. Okay, then we draw this curve. Now from this triangle. Yeah, you know, if now half part you see, yeah, of machine 1, this machine A side you see, yeah, this part only you see. There is a two triangle. This is small and big. Hello, there is a two triangles. They have a common angle. Correct, no? Like this. This is the common angle for both. So if two triangle has a common angle, means their ratio of side, like base to height ratio, is constant. Okay. So now we can write here for machine A. Hello. What we see, if small triangle to big triangle, so this is 1000, this is total load is 1000. Sorry, and total load is 1000. And this part is this part from here to here. Okay. It is 1000 minus X. Okay, so now this is X, this is 1000 here to here, and this height, base of large. So now small triangle to big triangle, base height to the, sorry, base of ratio of their bases to ratio of their height. Now height ratio is, small triangle height is this 2, so big triangle height is 2.48. Same like for machine B also. Small triangle is 10,000 minus X by big triangle is 800, equals to their height again. It is because they have a same group, na, that's why their this height are same. Okay, like this height is 60 minus X to 2.8. Now this is equation 1, this is equation 2. If suppose here na, in equation 1 and 2, the left hand side is same. If it is in the different group na, setting, then this is not equal. In that case, what you do? You have to do the cross multiplication. Then you get a two simultaneous equation in X and F variable. When we solve these two equations, I mean, you get a X and F. Then we can calculate the busbar frequency and load on machine A and B. Okay, but here it is more simple. Here both are equal now. So we can write from 1 and 2. equation 1 and this x by 1000 equals to 1000 minus x by 800. So this here 20 cancel. X by 10 equals to 1000 minus x by 8. Now you do cross multiplication, then 8x equals to 10,000 minus 10x. Or it
Sir,
is
वो 60 minus f है 62 minus f है
62 minus x आएगा.
yeah. Correct, sorry. Then it is 18x equals to 10,000. Then x equals to 10,000 divided by 18. Okay. 10,000 divided by 18. So it comes 555.5556, you can add kilowatt. Now this is the load on machine A, and B, on B it is 1000 minus X means 555.5. So it comes
444.
triple four. Sorry. 444.44 kilowatt. If you add now, you get 1000 total load. Okay. And here it is not asked frequency. If they ask na frequency, you put a value of x, this x in equation 1. Okay. If here we put the value of x, you get a f frequency also here. What is the frequency at this point? Okay. Yes. Here frequency, operating point. Okay. Okay, dear.
सर जो थ्योरी के आंसर क्वेश्चन है उसके आंसर डालना सर एक बहुत रजिस्टर है
ये वो एक सिस्टम से रिलेटेड पूछा है, उसका है नहीं वो।
ओके सर
वो जो ब्लॉकबस्टर ना,
ये सर
उसका कोई टैग स्टैग आपके पास रहेगा, कोई एसएलडी, वो प्रैक्टिकल क्वेश्चन है दैट इज एक्चुअली।
ये सर
सर जनवरी के बैच के लिए कौन कौन से टॉपिक कवर हो चुके हैं अब तक?
जैन में हम लोग मैक्सिमम डीसी मशीन, इंडक्शन मोटर, ट्रांसफार्मर मेजर तो कर, वी कवर द मेजर पोर्शन नाउ, ओनली some power system related and like your electronics portion is only left.
Sir, can you please share the last 5 months written paper, sir? And
Yeah.
sir, I have shared a question in the ETO active group. Can you please find the answer for that one?
Okay.
It's question number 2.